Okay, for the second part of lesson 7.2, we're going to use combinations and permutations to find probability. So we can use those to figure out how many outcomes there are total, or how many outcomes we want, and then we can turn those into a probability by putting them in the fraction. So questions you want to ask yourself are, does order matter? Because remember, that's going to determine whether it is a permutation or a combination. And we're going to find the number of outcomes, total number of outcomes, and the favorable outcomes, the ones we want, and then we'll turn that into a fraction. So here's our first example. Each student received a 4-digit code to use the library computers with no repeating digit. That's important. Fred received the code 7654. What is the probability that he would receive a code of consecutive numbers? First question, is order important? Yes. If I don't have the numbers in the right order, then I don't have a code, and it's not going to work. Find the number of outcomes in the sample space. So if I have a 4-digit code and I can't repeat my digit, how many options are in there in the first place? 10, and then I've used one, I cannot repeat it, so 9, 8, and 7. I could also do 10 digits, and I'm picking 4 of them. So this is where the permutation comes in handy. Because order matters, I would use a permutation, not a combination. So we can do 10p4 and multiply these outcomes either way. The answer is 5,040. So there are 5,040 total different combinations with 4 digits and no repeats. We want the favorable outcomes. The favorable outcomes for him are, let's see, they just have to be consecutive numbers. So let's start making a little list of consecutive numbers that could be my code. So 0, 1, 2, 3, 1, 2, 3, 4, 2, 3, 4, 5, 3, 4, 5, 6, and so far. 4, 5, 6, 7, 5, 6, 7, 8, 6, 7, 8, 9, and it could cycle through. So 7, 8, 9, 0, 8, 9, 0, 1, 9, 0, 1, 2, and then I would be 0, 1, 2, 3 back at that beginning. And so there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, no, those wouldn't be consecutive. If you're going, so we're only counting these, sorry, 1, 2, 3, 4, 5, 6, 7. So we're only counting these 4, because if you do 8, 9, 0, 1, that's not really consecutive, because it's, anyway, not going up anymore. That's 7, that's a 7. These also could be going down instead of up. So I could basically flip them all over and I would get the same. So if I took them all over, that would have 14 different favorable outcomes that have 4 numbers in a row. All right, sorry for the confusion there, but that's pretty much it. Now we just turn this into a probability. The number that I want divided by how many total possible ways there were. We can reduce that fraction. 14 actually goes into that 360 times, or we can divide that 0.0027 with the 7 repeating. So either of these answers are correct. So now we have an example that looks like maybe we're going to have something to do with area, because we've got this circle with shaded in parts. We have 3 semicircles with diameters 2, 4, and 6 centimeters, all arranged as shown. If a point inside the figure is chosen at random, what is the probability that the point inside the is inside the shaded region? So there's 2 things I need to look at. Remember the favorable, and that would be the favorable region would be the shaded, and then also the total. So the total region is going to be the area of the semicircle with a diameter of 6. So let's talk about area of a circle is pi r squared. Since we have a semicircle, we're just going to divide that by 2. So for this one here, the big one, the radius would be 3. So that would be pi times 9 over 2. That is my total area. So 9 pi over 2. Now, in order to find the shaded part, I'm going to take the whole thing and I'm going to subtract both of the other two areas. So let's just take each one of those little circles, semicircles. And so this little one has a radius of 1. So pi times 1 squared over 2. And this one has a radius of 2. So pi times 2 squared over 2. And I just went ahead and left it like that because we're going to have to subtract anyway. So 9 pi over 2 minus 1 pi over 2 minus 4 pi over 2 is 8 minus 4 is 4 pi over 2, which is 2 pi. So the area of this shaded part is 2 pi. I'm still not done because now I need to answer the question, what is the probability? So now when we switch to probability, the probability of the shaded part is what I want, 2 pi, divided by 9 pi over 2. So to divide that fraction, I would do 2 pi divided by, but when you divide, you can flip your fraction over and multiply. That's a 9. And when I multiply, I can cancel out my 9s. So I get 4 ninths. So the answer for the probability is 4 ninths, or 0.4 repeating. Let's do one more of those. If you want to try this on your own, again, you may pause the computer is being slow. You may pause the video and try it on your own. Here we go. This time we have some rectangles and squares. If a point inside the figure is chosen at random, what is the probability that the point is in the shaded region? So first of all, I like to do the total region first. The total of this one is nice and easy. It is a 9 by 9 square. So the total region is 81 square centimeters. Now, the part that I want is going to be a little bit trickier on this one. Let's see. There's lots of different ways to visualize this. So you can find the area of it however you want. We could just do 1/2 times the base times the height, because we know the straight up and down height is 9 also. So 1/2 of 81 is 81 halves. Just leave it like that. That would be the triangle, but we don't want the door, so, or whatever that thing is, so we need to subtract. It's 4 by 3, so we need to subtract 12. So 81 over 2 minus 12 is the favorable part, and we can turn that into a decimal just for easier use, 28.5. So the probability of the shaded region is 28.5. Oh, goodness. My decimal got ahead of me in my computer. Okay, 28.5 divided by 81. And we can just divide those and get 0.352. So this would be the probability that I'm looking for on this problem. Alrighty, one more slide here for lesson 7.2. We are going to talk about experimental probability. So I mentioned this at the beginning of lesson 7.2. Theoretical probability is mathematically what should happen. Experimental probability is what actually happens when you go to do the thing. So when you go to roll a dice, you don't necessarily get a 3 exactly 1/6 of the times. Sometimes you actually get 3 3s in a row. You never know what's going to happen with flipping coins and rolling dice and all that kind of stuff. So experimental probability is not what we want to happen, but what actually happens. And you can do a whole bunch of trials. You can do 10 trials. You can do 100 trials. You can do all kinds of different things. So let's go ahead. You can do this on your own if you want. I've got an example here from rolling the dice. So it says roll a 6-sided dice 10 times. So roll a 6-sided roll a dice and write down your results 10 times. Here are my results. I got a 3, a 6, a 1, a 4, a 2, a 1, a 4, a 3, a 2, and a 3. So you can see that I did not get even all the numbers on the dice. Let's find each of these probabilities. Well, we know from earlier that the probability of getting a 3 would be 1/6. But in this example, how many times did I get a 3? I got a 3. 3 out of the 10 rolls. And that is not the same thing as 1/6. But it is the correct answer for this problem. So on experimental probability problems, you might not get the same answer as your neighbor. What's the probability of getting an even number? So let's see, how many even numbers do I have? 1, 2, 3, 4, 5. Well, that's nice. 5 out of 10 is a half. That's probably going to be the same as its theoretical probability, because half of the numbers on a dice are even and half are odd. What's the probability of not getting a 5? Oh, there's no 5. So what's the probability that I don't get a 5? 100%. Or you can just 10 over 10, or you put 1. I just kind of like to think about that as I have 100% probability of not getting a 5 because I didn't get one. And that concludes lesson 7-2.